Okay, we are seeing this diagram where we list 9 elements, as you see, that we are going to need to model systems. In this case, you see at the top two sources here. This is a source of effort and a source of flow with the symbol SE and SF. We also see two connections, one for the kind of connections that have a constant effort junction and the one that has a constant flow junction. The three elements on the left over here, some energy storing elements like the I and C, and they are dissipative elements in this case, like this one. So we have the I element to store kinetic energy. Then we have the C element to store potential energy. Then we have the R element to store, or not to store, but rather to dissipate energy. All these are called single port elements because they interact with the system in a single port. But these two on the right hand side, they are two port elements, and they are the transformer or the generator. Okay, so those are the elements that we have to do modeling and simulation. Let's take a look at this slide. This is pretty nicely done in such a way that it'll explain clearly how the power goes from A to B with this Havaro, how the power goes from B to A depending on this arrow. Now, if you add to this, because what you have on the bottom is in addition to this. In addition to this, what do we have on the bottom? In here you have that A applies the effort to B, B responds with the flow. In this case, B applies the effort to A, and A responds with the flow. So this would be the effort side, and this would be the flow side. So if you are looking at this picture, let me where is this one. If you look at this picture, it means that the effort goes from A to the effort goes from B to A, and the flow goes from A to B. So in this symbol we have two possibilities, that the effort goes this way or the other way. Okay, now we have the connections in here, which we should also pay attention. Remember what I briefly mentioned about the constant force or the constant velocity? Yeah. In this case, you connect it this way, and in this case, you connect it this way. The other elements are the same. Okay.
I have a question. What are the 1 and the 0? And how do you explain the difference
the connection between the 1 and the 0 is the type of connection. This one or this one.
Okay.
All right. So this one, it has a constant force, so it's like this. This one has a constant velocity, so it's like this.
How do you know that?
Because if I move this, these are going to follow. So no matter what I do to M, K and B will follow.
Isn't that the same with the other ones you,
What do you mean, this one?
yeah, whatever you do to M, it's gonna affect K and B.
Oh, no, K and B is the opposite. K and B will determine what the matrix is, what the equations are. So in here you have one force that is applied and the mass moves with all the other elements. So that's why you have this AC and this like this. One yeah. So in here it's the type of connection that we're concerned with. All right. Now what I would like to do is to take a look at the different elements, and we are going to start with the R element. The R element is an element that whose characteristic is a relationship between the effort and the flow. So relationship between the effort and the flow means in an electrical system reflection of the a, like a resistor in or a damper on a mechanical system. That's what it means. So it dissipates energy. Now you could represent this element several ways. One of them is like this. Now when you have it like this, it is very obvious that this symbol represents this equation. This symbol represents this equation. How does it do that? You see, from the element, this is like the output of the R. And the F element is the one that returns to R. Okay, in here you have the equation the other way. You have that flow is 1 over R times Z. So, okay, there we go. If you could represent that in Simulink format, this is what you'll see. That Q times 1 over R is F, or that F is the input in this case. Yeah. Okay. So these are the R elements. On the right hand side is the bond graph notation. On the left hand side is the block diagram notation. But I want you to notice how the variables are. And where are those variables represented over here? Let's just do that. Like for example, in here, if I can make some notes, this I can say this is the effort right here. This is the flow, see? So this is saying to me that the output of R is the flow. So that means that F is equal to 1 over R times, yeah. So this is 1 over R times this, yeah. Let's go to the other elements. This is the capacitive element. This is static relationships between the effort and the displacement. Remember, this is like Hooke's law. That's how you remember easy. Force equals to B times X dot. Okay, so characteristic relation between the effort and the displacement in this case. For the C element, we have a little more of a challenge because this is the one that does integration. So on the left hand side, you can see this C element has the equation E is equal to 1 over C times the integral of f dt, or 1 over C times Q. So whenever you see this form of the equation, you know that it's a C in integral form. And then finally dq dt is the f, is there, yeah. Now, if you do it to the one on the right side, you're gonna see that this is, you have the f is equal to c times d dt is the derivative form. Do you see how you end up with derivatives on the right hand side? When you compute things on a computer, those are a little troublesome because you want them on the left hand side to be able to do the full integration. But you see here you end up with the derivative on the right hand side. Examples of this element: spring, capacitor, hydraulic system like a tank, or on a rotational system would be a damper as well. So this is a C element. Then you have, that's the representation that we saw. The inertia element. In this case, the inertia element has a direct relationship between the momentum and the velocity. See here, inertia element. This is the velocity is momentum relationship, 1 over I times P, or 1 over I the integral of P dt. dP dt is equal to, this is very important. And then you have that in the other side, E is the output, so everything needs to be put in terms of that. So E is 1 over okay. Do you see here how you end up with the derivative on the right hand side? The I elements would be like this. The I elements also produce integral form and store kinetic energy. So this is how that I element is represented. And then you have the two sources, which are also easy to recognize. Like you have the effort source for a voltage source. You have a velocity source on the bottom of this suspension. And it has to be a velocity source because if that's the model of a suspension of a vehicle or so, you're forcing the suspension to follow the profile. And in doing that, it says you must follow this direction no matter what the force is. So that's this concept of the causality, causal. And we saw that it determines how the equations are written. But right now, we're just going through the different elements. We have gone through two junctions. We have gone two sources, an I, a C element, and now we're trying the SE and the SF right now. Okay, in this case, do you see the element on the right, on the left-hand side? And here, what is the output of the SE element in here? So anything that is output is away from the element. Anything that is input is together. So in this case, you have that the effort source is what's important here. The flow is not. I think in fact we're saying it's mainly a effort source, not a combination of effort source and other things. Flow source, you represent it like this. Okay, so you have the two sources, the elements, and now let's move on. This again, perhaps a little bit of a warning here. When you pick up a source in Simulink, they assume it's either a effort source or a flow source. Example of effort sources: voltage, torque, input, force input. Examples of flow sources. Like following the profile or velocity source, and the same thing could be true for the rotational systems. So we have cover the two sources. Now, one thing I wanted to say is that when you go to Simulink and use one of these blocks, the other might be suppressed because it is assumed to be zero. But we know that the effort and effort sources and other elements interact with each other using the bond graph notation. So I'm just saying that in case you're doing it manually, when you go to Simulink, you don't need to put two signals. It's important because I have received that question in the past. Transformer element. In the case of a transformer, you have, see, the best example I can give you is a set of gears. Isn't it true that a gear set transforms one velocity into another velocity, right? Or one torque into another torque? That's what you learn in your design class, right? So in the case of a set of gears, you have the transformation of one velocity into another through the gear ratio. In the case of this lever, for example, you have the lever ratio, and that is the relationship between the velocities or the relationship between the forces. You have also let's see, gears are good, levers are good examples. In this hydraulic ramp is a very good example. This one is especially interesting because on one side we have the mechanical side, and on the other side we have the hydraulic pressure side. This example that you see on the board is very similar to the system used in the brakes of your car. Because when you stop, you push a little piston like this inside the master cylinder of the brakes on your car, and there's also in there other, let's say, other tubes, that go to each wheel, and from the master cylinder, they distribute it evenly to all four wheels, and that's how your vehicle stops. It has one of these hydraulic ramps. Okay. Any question? The transformer element could be written like this. You have that the symbol on the left-hand side here indicates that this is the input on this side, this is the output. And on this side, this is the output, this is the input. Yeah?
I think you might need to stop the recording.
Oh, thank you. Let me just do that so that we break it down. So we have the transformer element, and on this one you have it on this side, and then it means this effort times this module is this effort. This flow times this is this flow. Same thing, flow times this flow. Effort times this effort. That's why E1 is equal to the M times E sub 2. And that F2 is F1 times M. And then you have this. This would be the block diagram representation of this. And then finally, we have, this is another way of representing the same element, but with the causality on this side. This means E4 multiplied by the modulo produces E5. Okay, and so on. finally, the gyrator element is the other one that we need to be concerned about.